We are starting a topic potential, free energy and equilibria. Please read chapter 17.4. Now we are considering connection of our voltage potential to delta G, the free energy. Work associated with transferring electrons is determined by total amount of charge in coulombs transferred and cell potential. So our free energy delta G, which is measure of work, is proportional to number of electrons to potential in volts and to Faraday constant, which is simply conversion factor. So we have electricity units, voltage, and we have energy units, joules, and we need conversion factor between them, which is Faraday constant, named after Michael Faraday. Number of electrons, it's obvious, just in moles. And sign of minus, that's again agreement showing sign of potential. If you remove this minus, you'll have all potentials opposite sign. Combining previously derived relation between delta G0, the standard delta G, and equilibrium constant, you can look back in a chapter on thermodynamics, the previous chapter, an equation related delta G0 and E0, we have the following. First, for standard condition, delta G0 will be minus NF E0. This is general case, this is just for 0. Now we can solve this equation for E0. You have delta G0 minus NF. Or you can write that delta G0 is minus RT, natural log of equilibrium constant. Then you have your voltage of cell, RT divided by NF, ln K. So it doesn't matter. If you have delta G, you can calculate K and E0. If you have E0, you can calculate K and you can calculate delta G. Back and forth. These are simple calculations, there's nothing to talk about. Now, how cell potential is related to concentration? If we have standard conditions on left side, all concentrations should be 1 molar. So in this our cell you have 1 molar zinc 2 plus and 1 molar Cu 2 plus. Then you can measure voltage of this standard cell. What will happen if we'll change conditions to non-standard? So we change concentration of zinc 2 plus and change concentration to Cu 2 plus. Now we can compare these two cells. According to Le Chatelier principle, forward reaction has greater tendency to occur, resulting in greater overall cell potential. Why it is so? Because you have smaller concentration of zinc in solution, so it will be easier to put more zinc 2 plus ion. It will be large concentration of Cu 2 plus in solution, so it will be easier to deposit this copper on the surface. As a result, again, overall cell potential is a larger number. Can we make it qualitative? Yes. Free energy, as you may again recall from the previous chapter, free energy delta G is delta G0 plus RT ln of reaction quotient. From the slide before, you have delta G minus NFE. So just hooking this number, we have minus NFE delta G0 plus RT ln Q. Now dividing all this expression by NF, we have E delta G0 divided by minus NF and RT divided by minus NF ln Q. Next, let's look at what happens. First term is delta G0 divided by minus NF. Now, this is simply E0 from our previous consideration. So we can write E equal to E0 minus RT by NF ln Q. This equation is known as Nernst equation after Walter Nernst. What is Q in this case? We write all half reactions as reductions, so we draw the line. Above the line will be concentrations all of products, so on the reduced side. Below the line it will be concentration all the reactants on left side. Next simplification. We usually work at room temperature. So we know temperature and we can calculate RT if we know temperature. Of course, we know meaning of F. So R we know, temperature we put 25 degrees Celsius, and we know Faraday constant, and we want to convert our natural logs to decimal logs out of convenience. In this case, we can put RT by F as 0.059 volts or 59 millivolts, or even less precise 0.06 volts. So we have a very good primitive approximation of Nernst equation. E is 0 minus 0.06 volts divided by number of electrons, decimal log of reaction quotient. Very convenient simplified formula. Now let's look at examples. Let's consider the system in which platinum electrode is put in solution that has Fe3 plus and Fe2 plus ion. We have Nernst equation for this system in full or in approximation way. Now we write half reaction in this solution. Fe3 plus ions take one electron to become Fe2 plus ions. Number of electrons N is 1. Q is above the line, what at the right side? Below the line, what's at the left side? E0 we can find from any textbook, and we have such an equation for next Nernst. 0.77 volts plus 0.06 volts log Fe3 plus to Fe2 plus. Instead of having minus, I put Q upside down. Next example. I have silver ions in contact with silver wire. What will be Nernst equation for this silver electrode? Potential will be E0 it will be differently 0 minus 0.006 divided by n log q. What is our equation? Ag plus 1 electron making Ag metal. Q is above the line. Molar fraction of silver in pure silver wire. It's 1. It's pure metal. It's solid. Concentration of silver ions is below the line. Now we can find E0 from textbook and write an equation. E is 0 plus, again we're putting upside down, so sign is changing from minus to plus, 0.06 volts log of concentration plus. This is so-called first type electrode plus log of concentration of metal. For any metals in solution in contact with their solid, you'll have very similar. Next example, concentration cell. Let's consider two exactly identical electrodes put in exactly identical solutions. So two half cells have the same concentration of copper and exactly identical copper piece. Now, if left side is identical to right side, it will be no current or no voltage here. Nothing happens. So, for standard conditions, 1 and 1 molar, potential of such cell is 0. The concentration cell of interest is constructed by connecting two nearly identical half cells, each of it based on same half reaction and using the same electrode. The only difference is concentration of one redox species in solution. Potential of this cell is determined only by difference in concentration of chosen redox species, or rather by ratio of these concentrations. So let's consider the cell on the right side. Here we have Cu2 plus small concentration, and here we have large concentration of Cu2 plus. To become in equilibrium, the system wants to reduce Cu2 plus here and to increase Cu2 plus there. So what happens? Copper solid makes Cu2 plus ion here, and copper ions are precipitating on this electrode. As a result, electrons are coming from this electrode to that, and we have visible voltage. Of course, again, the system wants to have equal concentrations at the end. So how we can write this? Very simple algebra obviously gives us standard potential of 0. Now, for Nernst equation, we have 0 as our potential of cell and 2 electrons. Log, you have two different concentrations. Because these concentrations are different, log of this ratio is not 0, and it can be calculated. Electrons spontaneously flow from half cell with lower copper ion to half cell with higher copper ion concentration. So the voltage is coming only as a result of different concentrations. The chemistry at the left and right side is exactly identical. It's interesting observation. You need only difference of concentration. You have voltage between them. And this is basis of lots of different biological systems. In biosystem, you have a membrane similar to our bridge, in electrochemical cell, and you have different concentration of potassium and sodium ions outside of cell and inside of cell, and they are channels that can transfer sodium and potassium ions. So there is gradient or difference in concentrations. Because of that, there is a voltage between them, exactly like in a previous example. At usual conditions, it's around 70 millivolts with minus sign. When nerve cell is stimulated, channels open, sodium ions coming into cell and causing potential jumping from minus 70 to plus 30 millivolts. Then potassium ions are coming out and bringing the situation back. The result is spike or change in electrochemical potential across membrane. In this way, not going into details, electric signal moves down the length of nerve cell and transmit the nerve information. So all our brain activity, as well as many other biochemical processes, employs concentration potentials. You're listening to me, looking at this picture. Your brain activity is described by changes in concentration cells in your membranes.